In this next chapter, we're going to look a little bit more carefully at radioactive decay and look at the concept of half-life. This is section 41.3 in the chapter on nuclear theory and radioactivity. So we have determined that nuclei that do not have a good balance between the number of protons and neutrons are radioactive. And therefore they give off other particles. Normally, what do they give off? An excited nucleus, some nucleus here will give off an alpha particle, a beta particle, a gamma particle. It could even give off a neutron. It's also possible for a nucleus just to split under certain circumstances. But for the most part, these are the types of radioactive decay that we have. This is, of course, 2 protons and 2 neutrons bound together as a helium nucleus. The beta particle is an electron. It could also be a positron under some circumstances. The gamma particle is electromagnetic radiation. And we know what a neutron is. The neutron can just be emitted from the nucleus, and that occurs sometimes. But now, talking about this, what we also want to know is what kind of lifetime, how often does this happen? Does this happen very, very fast or very, very slow or whatever? Well, if we have a substance that disintegrates, one of the important concepts is the concept of a half-life. Well, why are we interested in the half-life? The half-life is the time it takes for half of what you have to disintegrate. So if you have a pound, and it takes a year for that to become a half a pound of that substance, then you'd say that the half-life is 1 year. Well, you can't say when it's all gone, because it's never all gone. You lose a half of it, then you lose a half of that, then you lose a half of that, in what is an exponential decay of the number that you have. In fact, it turns out that the number that you have of a given atom is the number that you started out with for radioactivity, times e to the minus gamma times lambda. I think I used lambda here. E to the minus lambda times t. And so if I know how many I start out with, like maybe 3 moles or something like that, then if I know this factor lambda, which is related to the half-life, then I can predict in the future how much I'll have. Now you remember that this exponential decay looks like this. So I start out with some amount n naught right here, and then n, which is this axis, goes down and down and down and decays more and more. So what we're interested in is how long does it take to get to half? And then in that amount of time again, I get to half of that. In that amount of time again, I get to half of that. How do we relate that to this thing right here, this equation? This equation is very important. This is also the kind of equation you'd have in germs that are being killed by some antibiotic. You put the antibiotic in your body, and you start out with so many germs, then after a certain amount of time you have half that many, then you have half that many, then you have half that many, each at equal intervals of time. That is called a half-life. If I went the other way with a positive exponent here, that would be called the doubling time. This is where you put your money in the bank and it doubles in a certain length of time. So how do I analyze this more carefully? Let me back that up. Well, I'm going to divide both sides by n naught. So I've got n divided by n naught. And you can see that that's a fraction. And I want that fraction to be 1/2. The number that I have now is half of what I started out with. So n over n naught is going to be 1/2. Now that's going to be equal to e to the lambda, e to the minus lambda, times what is called the capital T, the half-life. We sometimes put t 1/2 there. Okay, can we solve this equation and find out what the half-life is? Well, this 1/2 is the same as 2 to the minus 1. And so now I can look at this equation and take the log of both sides. If I take the natural log, then the natural log of e to the minus lambda t 1/2 is exactly minus lambda t 1/2. And the natural log of 2 to the minus 1 is minus 1 natural log of 2. It's kind of going off the page over there. The minus signs cancel on each side. And so what I end up with is the half-life is equal to, remember this minus 1 cancels this, So I divide through by lambda is equal to ln2, the natural log of 2, divided by lambda. So 1 over lambda is about equal to the half-life. Why? Because the natural log is based upon 2.71818 and so forth. And that's kind of close to 2. I mean, it's not really, but it's reasonably close. So lambda is very strongly, 1 over lambda is very strongly related to the half-life. To do it exactly, you take the natural log of 2, divide by lambda, and that gives you your half-life. That also tells you that the units of lambda are inverse seconds. Why is that? Well, you know it has to be inverse seconds because your time here, well, normally would be in seconds. So this lambda has to be 1 over seconds because the argument of any transcendental function has to be dimensionless. You can't have an exponential of something that has units. So these units and these units cancel, so it's dimensionless. And that radioactive decay comes, in fact, from a differential equation where the change in the number with respect to time is equal to minus lambda times the number I start out with times dt. In other words, the change in the number at any instant is the number I had that I began with. I put an end naught there. It really shouldn't have an end naught. That should not be an end naught there. So the change in the number is proportional to the number and the amount of time, the infinitesimal time. And of course, by bringing the dt over here, I get dn dt is equal to minus lambda n, and that's a differential equation. And if I solve that, I'm really saying what function is such that the derivative of the function is proportional to the function itself, proportional to the function. And the answer is the exponential. And so this is the solution to that differential equation. Now, I've already taken both sides and done that done that computation and related the lambda to the T1/2. Now, radioactive dating is something you're very familiar with. Carbon-14 has a half-life of 5,730 years. 5,730 years. That's for carbon-14. Of course, carbon is 6. Has 6 protons, 14 protons and neutrons. So this is not like carbon-12, which is your normal carbon. This is something that has too many neutrons. Therefore, it's very likely that this thing is radioactive. So if I have a kilogram of carbon-14, in 5,730 years later, I'll have half as much, half a kilogram. Then I'll have a fourth of a kilogram that much later. Now, the reason that this is very important is that we take in this carbon-14 while we're alive. That's for plants, for anything else out of the atmosphere. But once we die, we take in no more carbon. We don't eat carbon food. The plants do not take in the carbon in their metabolic cycles. And so what happens is the amount of carbon is frozen at the point of death to be that's stable in the atmosphere. And so now your carbon-14 decays, so you can see how long it's been since that tree was alive, that if you look at archaeology, or that person was alive by looking at their bones, and you can date things using carbon-14. Incredibly important, can be done very accurately. Now the becquerel is a unit of radioactivity, which is 1 disintegration per second. And you need to know these because in the medical sciences they're extremely important. 1 disintegration per second. That means 1 atom every second. That means you have 1 becquerel of unit of activity. Well, the Curie goes back a lot before that. If you have 1 gram of pure radium, then it has 1 Curie of radioactivity. Well, it turns out that 1 Curie, Ci, is equal to about 3.70 e to the 10th becquerels. Wow, that is, we can see here that if we have radium, if we have 1 gram of radium, this is for 1 gram of radium, 1 gram of radium is going to give off 3.7 times e to the 10th. What is that? Well, e to the 9th is a billion. That's 10 billion. That's 3 That's 37 billion disintegrations every second for 1 gram of radium. That is a huge amount. If you had a kilogram of radium, it'd have 1,000 times that much, or another factor of 3 here. So that is the huge radioactivity for something like radium. And of course, the people who worked with early radioactive materials actually were wearing gloves because their fingers would disintegrate and their flesh would fall off from the radioactivity. Very horrible type of thing that we learned, that you had to be extremely careful with radioactive materials. These people basically devoted their lives to that and lost their lives to some extent because of the radioactivity, and the dangers of that were not known for cancer and for other things. Your takeaway here is knowing this half-life, understanding it, understanding the units of the Curie and the Becquerel, and understanding carbon-14 and how that's used for dating.